Okay, welcome to our session in regression analysis, where we're going to discuss linear regression, linear correlation, and the significance tests under the T distribution using samples less than 30 and under regression. Then lastly, for the other session, we'll discuss multiple regression. So to start with, regression analysis is mainly about relationships that are typified by what is called a dependent variable against an independent variable. A dependent variable against an independent variable. So we need to first understand what is a dependent variable and what is an independent variable. So as you can see from this equation, an independent variable is what causes the variation in the dependent variable. So the relationship that exists between x and y is that of a causal relationship. So the independent variable causes dependent variable to alter. It confers what we call causality. So if we're going to look at two variables, for instance, advertising and sales, sales depend on advertising. Unlike the other way, advertising cannot depend on sales. They're independent. So from the terms dependent and independent, that is how we can define them. Now, under this topic, we need to understand issues of corinality, because this is one key aspect, not only for this topic, but also for your research. You must understand that quantitative methods is a very key topic, it's a key course, because it hinges upon all master students in understanding their research. You want to identify the relationship that exists between performance and the motivation. That is all an issue of regression analysis. So to find the relationship between x and y, we need to use regression. So the regression equation is also called the prediction equation. Using the prediction equation, we would want to see how much of x predicts y. So the independent variable x is called the predictor, and the dependent variable y is called the predictant. So you need to understand it from the word go, because this is not only for academic purposes, even for application purposes. The predictant is y, and the predictor is x. So using a linear regression equation, y is equal to the autonomous coefficient here, which is a0 plus a1x. This is the same. Our a0 is the same as our a itself, which is called the y-intercept, the cutting point of this axis. Then we have our slope, which is b, or a1 in this case. So we understand linear regression with also other variables called the correlation. The correlation is a key term that we use in regression, which measures the strength and direction of the relationship between two variables. So we have the correlation of coefficient and the correlation of determination. R squared is the correlation of determination, which measures the percentage of the variation in the values of the dependent variable that can be explained by the variation in the independent variable. and our R squared must always range between 0 and 1. So if we have a value, for instance, 0.7654, it means that 76.54% of the variation in y can be explained by the changes in x, meaning the remainder, which is 23.46 of the variation in y, is presumed to be due to random variability. If this was R squared for sales against advertising, we would say 76% of the sales are rising from the advertising efforts that were enacted by the advertising department or the marketing department. But the remainder, the 23% of the variation, was due to random variability. Now, we also have another R value, which is called the coefficient of correlation. That one just gives us a picture of whether we have positive relationship or a negative relationship. Under regression analysis, there's also what we call the significance of the regression coefficients. We need to test using the t-test, using a hypothesis that there is a relationship b is equal to 0 or b is not equal to 0. Our gradient is what we use to test. Now, you realize that we use a t-test because most of the values that we use are a pair less than 30. The significance of the regression coefficient is the most useful way to test the significance of the regression using what we call analysis of variance, which represents a total variance of the dependent variable into the two independent parts. Now, we're going to look at the formulas that we use. There's what we call SSYY, which is the variation in y, SSXX, which is a variation in x. You can also use what is called the variance analysis. But for now, I want to dominate on how to calculate the regression equation using the following question. So the following shows the number of hours of 6 students who studied for a final exam, and their scores were as follows. Those who studied for 3 hours got 86, 5 hours, 95, 4 hours, 92, etc. So you are being asked to calculate part A, the correlation coefficient between hours and the exam score. Then part B, you are being asked to test the significance of the correlation between hours and the exam score at 5%. Okay, so regression falls under hypothesis when you're testing. When you're calculating the correlation of coefficient and correlation of determination, we use the following formulas. Okay, so you would itemize your figures x and y, where x is standing for the what? For the hours of study, and y the exam score. So you multiply x and y to get xy. You square x column to get x squared, and y column to get y squared. So when you do the summations here, these are the figures we're getting as the totals. Now, having gotten the totals, you need to also understand the sample size, n. N, you just count the number of pairs that we have. We have 1, 2, 3, 4, 5, 6. So there are 6 pairs of data paths. So this is our n. So we will use a t-test if we're going to measure the significance of the correlation. So we've been asked to calculate the correlation coefficient and also the correlation determination. The correlation coefficient simply is used to ascertain whether we're having a positive or a negative relationship. So the formula we're using is n summation of x, y minus summation of x, summation of y, everything over n summation of x squared minus summation of x to the power 2, brackets n summation of y squared minus summation of y to the power 2. So where we have our n, we put the 6 xy from the table. These are some sum totals. So this is summation of x, summation of y, summation of xy, summation of x squared, and summation of y squared. So it's an issue of just substituting these in the formulas. So this is what we did. Our 6 here, our 1835, 25, 21, and 516. We simply substitute the figures in there. So when you substitute the figures, our error is 0.862. Before I proceed, unless there are any questions at this point.
Okay, so since we are saying that when we are trying to find the correlation, we're trying to see the relationship if it's positive or negative, and that it should be between 0 and 1. So with this figure that we have, can we say this is a strong correlation or what?
So correlation here.
To add on what Anne is saying, I would also want to find out, because I think from our last the previous lessons that we did with you when you were in Osaka, you did show us how to tell the relationship actually from the graph. But I see from this illustration, there's actually no graph or anything of the sort.
Okay, so even without the graph, we're able to tell the strength of the relationship and the direction of the relationship. What we've just calculated is just the direction of the type of relationship. Here we're only interested in the positivity or negativity of the regression. So our error is 0.862. When you square it, that's when we're able to tell whether it's strong or weak. So let's try to square this. And what do we get?
Zero 0.743.
0.743. So what does this mean? 0.743?
It's a strong correlation. There's a strong
Yes, but specifically, it means 74%.
So what we have found now is the coefficient of determinant, right?
Yes, of determination, yeah.
Of determination, okay.
So this one here is just telling us that the relationship is positive. Now here, this one is telling us a strength. This is a strong relationship. It's 74%, 74.3% of Y is influenced by X. So this is now where the strength is coming from. So even if we have not drawn, we know that it will be a positive relationship, which will be upsloping, and the dots will be somewhere like that there. But this is not too scary. I'm just giving you a picture of how it would look. Any other questions?
Could you just reiterate what you said about the coefficient of correlation?
The R is coefficient of correlation. It just tells you that there's a positive relationship. The R squared is a coefficient of determination. It is a predictor. It
But
gives
in
you
terms of
the
what
extent.
being, sorry, maybe I should have asked it like this. In terms of it being negative or positive, where there is no slope, where you don't read it from the slope, because our other exercises were a bit straightforward compared to this, in my opinion. So where there is
All
no
right,
graph
so
like, how do
the,
you tell that that's positive or negative?
the slope and the R go together. If your R is negative, your slope is obviously negative. If your R is positive, your slope is also positive. All right, so here our R is 0.86. It's a positive. It's a positive relationship. So the slope and the R would help you give you the direction as to whether it's a positive or a negative relationship. But R squared is the strength of the relationship. Okay, now let's go to testing at 5%. Now, when you're dealing with regression analysis, you need to know that there are 4 types of relationships, if not 5. You have a positive, strong, you have a positive, weak, you have a negative, strong, you have a negative, weak, and you have no relationship at all. So if you're testing for the significance of the regression equation, you're testing if there's a relationship and if there's no relationship at all. So if the regression equation is significant, you are going to accept our H1. So what we are trying to do now is to test the significance of the regression equation. So our null hypothesis will state the gradient is equal to 0, the gradient is not equal to 0. The gradient is equal to 0, meaning there is what? No relationship at all. The gradient is equal to 0, there's no relationship at all. There's no significance of the test, in short. Here it is significant. So whenever we reject HO, we're trying to say that there's a significance of the slope. So we found our R to be what? 0.862. Now I want to use the t-score to test the significance. So to test the significance, we're using t is equal to R root 1 minus R over 2 and n minus 2. Our R is 0.862, 1 minus 0.862 squared over n, which is 6 minus 2. When you do a computation, we get 3.4. Now, our decision rule will be to reject if this is our accept region and this is the rejection region. Now, how do we read the t-test? The t-test I reiterated in the other classes to say if you are dealing with 2 samples, step 1, find the significance level. Our significance level has been given as what? 5%. Step 2, divide by 2. Since it's a two-tailed test. So what is half of 5%? 2.5%. Step 3, if it's 1 sample, we're going to do what?
Degree of freedom.
The
We
degree of
subtract
freedom,
1.
n minus 1. If it's 2 samples, what do we do?
N plus n minus 2.
n1 plus
N1 plus n2
minus
minus
what?
2.
So what was
2.
our n1?
N1 was, is that 6? Yeah, they're all 6, 6.
Okay.
Yeah.
But in this case, we're going to consider it as what? Our n. What is our n in this case? How many
N
we
was
have?
6.
Yes, our pairs. Yeah. Okay. Our pair, we're going to say 6, right?
Yeah.
So we're simply going to say 6 minus 2. What do we have?
4.
4. So we're going to check 5%, 2.5, under 4. Okay. 5%.
Come on, sorry. Why aren't we saying 6 plus 6 minus 2? Or we're just considering them as one is x, the other one is y.
Yes, because our n in this case is it's the average of them. Our n in this case is 6. Okay.
Oh, okay.
So we're going to check under 5, 2.5, under 4. What is the reading? 2.776.
Yep.
2.776. So when we go to our t table, we're dealing with negative 2.776. Here we have 2.776.
7, 6.
So our t calculated was found as what?
At 3.4.
And where is 3.4?
It's inside the AR.
No,
Oh, away. It's away. Sorry.
the rejection region.
It's in the rejection region.
So in this case, since it's greater than this, what are we going to conclude? We're going to reject HO. Okay. And we will agree to say that the coefficient of correlation has a significant relationship on the exam score. So we conclude that the population correlation is not equal to 0. There appears to be a significant, here you need to use significant, relationship between the number of hours studied and the resulting exam score. So I was trying to iterate to you to say, by accepting HO, it means the pi feed H ticker, there's no significant difference. By rejecting H, it means yes, there's a significant difference because the slope is not equal to 0. Remember, whenever the slope
Yes.
is equal to 0, it means there's no relationship at all. The graph looks like this when your R is equal to 0. This is what it means here. Here, R is not equal to 0. There's a relationship. Konsoku, there is not equal to 0. There's a relationship. That's what it means. Okay, so this is the simplest way you can use a T to explain. So I'll take you through another question where we'll be asked to test the difference between mileage and the price. Here, we're going to look at 3 key things. Number 1, how to come up with a regression equation. Number 2, how to use a regression equation to predict. Number 3, how to come up with the sum of squares and to use the coefficient of determination to interpret the relationship. Now, this is a very basic way compared to the way we looked at it, because what we did earlier was even more detailed than this. All right. So like we said, you need to identify your dependent and your independent variable. X is our mileage and the price is our Y. So the mileage is what determines the price. The price cannot determine the mileage. So sometimes if the examiner wants to be cruel, he may swap them, but you need to know what a dependent variable and what an independent variable is. All right. So we'll go to our workings. So looking at our workings, x, y, y squared, this is not an issue so much. We find our summation of x, summation of y, xy, x squared, and y squared. So using this formula, there are three formulas that we use to calculate our slope. You can use any of them. Remember, the whole lot of this is called summation of what? xy. The whole lot of that one is called summation of xx. So if you're going to use the sum of squares separately, it's still well and good. It will give you the same answer. xy gives you -3, 1408. The x gives you 28, 848. When you divide this is giving you -0.118. Already, this is telling you the slope is negative. And without much ado, you would still tell that your R will still be negative. R squared can never be negative, but your R is negative, even from the slope. And when we go to calculating our A, which is the y-intercept, the formula is standard. Summation of y over n minus b, summation of x over n. So in the b, we're going to use the formula that we had here. Then summation of y from the totals that we've had. So it will give us our final answer of A as 17.681. So you substitute here on the A, you put 17.681. On the B, you put -118x. So having found the regression equation, you are now being asked by the examiner to predict the selling price. So find y if x is what? 50,000. Find y if x is 50,000. You need to be careful the values you're getting here. If you're zeroing out, you can simply simplify by scrapping out the zeros here, but make sure that you bring them out after your calculation to reduce on your on your zeros here. You can scrap out the zeros there, so that if you're putting them in the regression equation, you're just putting a 50. All right, and after the final answer, you put back the zeros here. So when you put a 50 here, because we scrapped out the zeros when you're calculating, our y here came out to be 11.781. This actual figure is supposed to be 11,781. So because of the zeros that we scrapped out, this is the final answer. So this is our price at the mileage of 50,000. This is clear so far. Before I proceed,
I just wanted to ask on the two formulas that are there for finding the slope. Yes, you mentioned that the one that he's given us in this case and this other one for summation of xy over summation of xx will still give you the same answer, right?
yes, it's the same. So B is given by summation of xy minus summation of x over summation of y divided by n, everything over summation of x squared minus summation of x to the power 2, everything over n. Now, the whole lot of this top part is called summation of xy. The whole lot of this bottom part here is called summation of xx. Using mathematical manipulations, you don't want to deal with fractions. You can just put this x here. This comes out to be n summation of xy is equal to summation of x times summation of y. Everything divided by this n now comes here. We have n summation of x squared minus summation of x to the power 2. So all these three formulas are simply going to give you the same answer regardless of whatever you use. This one here, 1, it's the same as this one here, summarized 2, or this one can be resummarized 3 here. So don't get confused, all these are the same. Is that clear? So this is the formula that we are talking about here. That is the slope formula.
Collins, the n is supposed to multiply only xy, right?
Yes.
Oh, okay.
Supposed to multiply on xy. So if you're going to use it here, it's only going to divide x times y here. So all these are the same ones. Here it's multiplying on xy. Please, that's a very good observation. Don't put these in brackets. Some people just want to multiply against everything, you know, it's just multiplying here. So this takes us to what? To what we computed here. So having found our A, we have a regression equation. We substitute the 15 there to get our price, expected value. Then now we've been asked to calculate the sum of squares. So this is simply the SS.
Total.
This is the sum of square total. This is also same XX YY. This is the sum of square total that we also use in the what? And Anova. SSYY is also the sum of square total, which is this value here. So we've been asked to find the sum of square total of the n, the eight pairs. So this is a formula I'm just trying from explaining to you. And you get asked to find the sum of square error. Sum of square error is easier found by finding the sum of square XX. Then you subtract from here. Yeah.
Okay.
Yes. Because this is a little bit more complicated. Just find sum of square XX and you subtract, because sum of square error, it never has a formula. It's just the difference. But if you like, you can go ahead with this one here. A summation of y minus b summation of xy. So this one here, our a is the gradient and the y-intercept, summation of y minus the slope, summation of xy. These, you can add them. When you subtract this from that, then the final answer subtract from there. All right. But when you subtract this minus that, the answer that will remain is the sum of square xx. Okay. Then sum of square regression is simply the difference from sum of square total minus sum of square error. Now, sum of square regression also has I think a much easier formula. SSR can be found by simply finding summation of xy over summation of xx. This one will give you the sum of square regression. It's easier like that. So when we discuss formulas, I'll have a class just to discuss formulas on their own. So sum of square total minus sum of square regression. Sum of square total minus sum of square error is giving you sum of square regression. This is how we find it. So take note of the sum of square error, which is summation of y squared minus a summation of x, a summation of y minus b summation of xy. When you get this, the difference between the sum of square regression, sum of square total and sum of square error will give you the sum of square regression. Then the r squared is given by SSR over SST. Sum of square, the coefficient of determination is given by SSR over SST, where I divide the answer we got here, the 50.27 over 71.5, which is this here. Now remember, you're not tied to this formula. If you cannot remember this, you still had the formula that we had at first that you could still use. The answers will still be the same. The first question that we did here, we calculated the sum of square, our r right here, then we squared it to get our sum of square, our coefficient of determination. So here, these are just using the values that we've just found here to find our sum of square, our coefficient of determination, SSR over SST, which will give you 50.27, then to give you this final answer here. So what does this mean? It means that 70.3% of the variation in the price is explained by the car mileage. He could have crossed over to show you how the Anova table for regression looks like.
Actually, I wanted to ask the same.
So Anova table, we have the linear regression always has 1 degree of freedom here. Then our degree of freedom for the error is n minus 2. Degree of freedom for the total is n minus 1. So when you have our SSR, we add it to the SSE, we get our SS total. When we divide 1 into SSR, it gives us MSR. When you divide SSE over n minus 2, it gives you MSE. When you divide the MSE into MSR, it gives you the F calculated. So we have an analysis of variance under regression that looks like that. I've sent you these notes already on the group. So this is where we end with our tutorial sheet number 10. I would love to also take you through a shorter route of this after this session.